tell more about this, what the return of the polynomial method. This is a recent result of with joint work with Mrinal and Prasad from TIFR and Madhu from Harvard. It's on an improved analysis for the classical line point low degree test. If you don't know what that means, let's get started. Let's see what the problem is and stuff. So basically, we've given issue, we are given this an underlying finite field, say of size q. An ambient, there's a degree parameter which we care, and we are going to be working in degrees for the entire of this talk. We can talk about of degrees which are, or we're only going to be talking of degrees smaller than q. You can't consider this problem even for degrees larger than q, but for this talk, we'll take ourselves. There's an ambient dimension m. Therefore, think of this as this vector space f to the m, and we're given a function as a table of values on this entire vector space. What we want to check is this function actually the evaluation of an m-variate polynomial of total degree at most d? You're given this function as a point table of values, you need to check it. Of course, this is an easy problem. If you are allowed to read the entire input, you just interpolate and check if this is indeed the evaluation of a low degree problem. What we want to do is we want to do this without even reading the entire input. We want to read the input at a few random locations and then be convinced with high probability whether the function at hand is a polynomial of total degree at most d, or is it does it look like a polynomial, or is it far from a polynomial? So that's the basic question we'll be looking at, and we'll be seeing various type of ways of checking this low degree. So of course, if you can get to see the entire input, this is an easy problem. In fact, they are nearly linear time algorithms which will do this for you. What we want to do is, we don't want to read the whole input. We want to read a significantly smaller fraction of it. How small? The small will be important. So, and we want to check this. So in this context, the first paper on this line was the line point low degree test suggested by Rubenfeld and Sudan in 1991. They just suggested the following. This one suggested just pick a random line L in the plane in the m-dimensional space. Query f on all points just on this line, not the entire this one, and then check if the restriction of this function along this line is the evaluation of a univariate low degree polynomial. Clearly, if the global function was low degree, was a multivariate low degree polynomial, its restriction to the line will be a univariate low degree polynomial. So clearly we have the completeness statement. If f was in fact a polynomial in the m variables of degree at most d, then the low degree test will accept with probability 1. What we're interested in is sort of the other statement. If you can show that this test accepts with some non-trivial probability, can we say that f somehow looks like a polynomial? That's the main thing we'll be interested in, is the soundness of this test. Say this test passes with some probability, say 99% or 1%, whichever. We look at all the parameters, settings. For each of those cases, can we say if f does indeed look like a polynomial? In fact, very soon after Rubenfeld and Sudan, the subsequent paper of Rubenfeld and Sudan, with follow-ups of Arora and Safra and Arora Motwani. So then secondly, these, if you notice, are the papers corresponding to the PCP theorem. They proved this following very strong soundness statement. They showed that there is some delta, let's say 0.1, such that for all fields of size at least cubic in the degree, the following holds. If the probability that the low degree test rejects is at most delta, is at most 0.1, then f is actually in Hamming distance very close to some polynomial p of degree t. So there's a statement they showed, as long as the rejection probability is not too large, then for every such small rejecting probability, you can show that the only reason the rejecting probability is small is because the function actually looks like a low degree, an honest to God low degree polynomial. Okay, and this sort of for questions. Yeah. This is the technical core, as mentioned. The proof of this was proved as part of the PCP theorem, and this formed the technical core of the original proofs of the PCP theorem. In fact, almost all proofs except when Edith intervened and gave another proof of the PCP theorem. All the algebraic proofs, the low degree test analysis, the soundness analysis is the technical meat of the PCP theorem. And this one? Huh? There's also some check, yeah. Check. And this has a very long history, more or less, the history of the low degree test more or less mirrors the history of the PCP theorem. And in fact, even prior to that, proof of MIP equals next and so on. So let's quickly, right? So this starts off with the work of Babai Fortnell, and one of the first instances of the low degree test comes there, where they don't look at all lines as we mentioned over there. They only look at axis parallel lines. And then Rubinfeld-Sudan suggested the line point test. And in the proof of the PCP theorem, Arora Safra and Arora Lon Sudan and Segedi actually proved the low degree test as stated in the previous one. So after that, Polishchuk Spielman went back and looked at the axis parallel test, and they actually showed a stronger analysis, which we'll see later on in the talk, stronger analysis for the axis parallel test, but with Q significant, the requirement on Q to be significantly low. Q was only linear in D and not cubic in Q. I haven't mentioned what the axis parallel test here, but this was some polynomial and they get it to be nearly linear. And then building on this, Friedel and Sudan in 95 further improve on the low degree test statement of ALMSS to give a low degree analysis in which Q is just linear in D. More precisely, this is the statement of the combination of Polishchuk Spielman and Friedel and Sudan. They show it's exactly the same statement we had before, except that now Q is omega T. And notice Q has to, for this setting of parameters, you need sort of Schwarzschild to hold good. So D by Q should be at least a small number, and this is sort of a requirement, and that's the only requirement of you require a few versus T.
Yeah. So do these improvements correspond to any noticeable improvement in the PCP theorem, for example?
Yeah, so in fact, Polishchuk, I'll come to that later, but Polishchuk Spielman, it was fact that this controls the rate of the code. So you got Polishchuk Spielman first gave the first nearly linear sized PCPs and polylogging. So that was the motivation for Polishchuk Spielman.
Yeah, just go to the next slide. Yeah, just to add the buzzwords to the many results we'll see. This, in some communities, this is called the stability theorem. And stability theorems, I think we'll hear more talks, maybe from Peter and others, about stability theorems. You have, when you are close to satisfying the obvious equation, like when it is a polynomial, you accept with probability 1. If you accept with probability close to 1, then the structure remains. That's a stability, not just you pass it, but structure remains.
Yeah, so these are stability theorems. In fact, we'll ask for very strong stability theorems. This is what I want to say is this is actually stability theorems in the lower regime. You're stating that if the thing rejects with a small amount of probability, then it is close to a polynomial. What about?
This is the same degree that you get at the end.
It's the same degree. The degrees are the same. So I will not specify the degree. There's one ambient degree parameter will be working, and that's the same degree.
No, I think you have something wrong. You want the degree except with delta probability.
No. This is the low error regime. This is the I haven't yet.
That's the stability.
This is the stability version. This is the usual stability version. What we'll ask is a slightly more this one. Suppose
Q question just before you move on.
Yeah.
Like just for reference, what happens when Q equals 2?
So I'm going to be working when Q is significantly larger.
I understand, but I want to know why this fails.
No, so firstly, reading a line, you don't get any information. You need to at least read such that you need to read an affine at least as many points so that degree D functions are not or do not capture every possible function. So in particular, if you're working with degree D over GF2, you should at least read a D-dimensional subspace or a D plus 1 dimensional subspace. And in fact, this is a test. It's the AKKLR test. It has been analyzed. That you can do it for GF2. So what you will to check for degree D, you will read a D plus 1 dimensional space and check that the restriction is a degree D function, and you have a similar analysis.
So the point is you have to modify the procedure, but it's very
But they're very similar to this. Very similar to this. Yes. Yeah. The statements are very similar. The proofs, each of them require slightly different proofs. Yeah.
I think I'm not understanding why axis parallel and general line, why they're different.
So axis parallel will only first give you bounds on individual degree, because you'll never notice if you check, whereas this one will give you control of the total degree. If you're only noticing axis parallel, you will never realize anything about total degree.
Thanks.
Yeah.
But you want that because there's much fewer axis parallel lines compared to all possible lines. So that means that the number of different things the prover needs to give you is small.
That's one thing, and also you can give a function which is low degree in all but one axis, one direction. So with probability for 1 minus 1 over m, it's going to pass the low degree test. But with there's just one direction in which it has a high degree. So unless you pick that direction, you will not realize it. So it will not give you an axis parallel thing will never give you a statement of this kind, unless your axis number of directions is constant. It's 2 or 3. If once you go to m directions, you will not get such a statement. You need to have in more directions, more number of lines passing through a point than one over m. Okay, so this is the usual. This is what this is similar to things studied in other places called the stability. This problem, if it's not so being low degree on a particular line is the property of Reed-Muller of these low degree polynomials. That is, this is a characterization, and it's a robust characterization. If you pass this most of the time, then you're also close to being a low degree. Now, actually, let's make life even harder for us and ask what happens in the other regime. Let's send the rejection probability all the way to 1, close to 1. Therefore, the test accepts with very small probability. Can you still say there is some structure underneath? That is, suppose the test passes with better than random, this one, significantly better than random, but still very, very small. It's not like out here where it's passing with probability, say 90% or so, but it's passing with probability just 1%. Can you still say there's an underlying structure in the function? And this was studied in 97 in 2 independent and parallel works by Arora and Sudan and Raz and Safra, who gave analysis of the low degree test in the high error regime. And this is going to be the focus of my talk. So let's go into what Arora Sudan and Raz Safra the results are. Let's start with Arora Sudan, sorry. The Arora Sudan show there's some epsilon naught. We'll come to this number, which is some ratio of this form, such that if the test accepts with some probability more than epsilon, this epsilon could be anything, then in fact there is a low degree polynomial with which the function agrees with probability at least epsilon minus epsilon naught. The agreement is just one minus distance. Therefore, if you accept with some non-trivial probability, then you actually do agree with an honest to God polynomial with reasonable probability, but for this extra epsilon naught share. So as long as epsilon is larger than this quantity, you do get some. That is, whenever the test accepts, that is because there is some underlying polynomial. There could be more than one such polynomial, which has good enough agreement. This is because you are well beyond the distance of the code. So there could be more than one such polynomial, but at least there's one polynomial which explains why the test is passing the probability also.
Also degree D.
Huh? Yeah, whenever I say polynomial, I mean going to polynomial of degree D. Yeah.
So where does tau feature into the conclusion?
Tau is just some, it's like 1 over 100 or something.
It's a fixed constant.
It's a fixed constant. I should have put that. It's a fixed constant. Yeah. Yes.
Like what's the probability that just a random function accepts?
1 over Q.
1 over Q.
1 over Q. Yeah. So technically speaking, you should be able to get these results for anything larger than 1 over Q or possibly 1 over root Q. So you can come up with this one. At least 1 over root Q. One should be able to. Right now, we're looking at epsilon being this one. I'll come to that. There have been results that studied that also. So this answers the high error regime, but for the caveat that Q has to be D power 4. So it's not like what the Polishchuk Spielman or Arora Sudan results gave. It doesn't give you Q which is linear sized in the degree. In particular, if you look at it as a code, the rate of the code is bad. So this was Arora Sudan. Raz Safra gave a different test in which they did get Q to be linear in D. But what they did was they changed the test. They modified the test from the line point test to a plane point test. More precisely, they said it's almost exact the same thing. You pick a random plane look at the restriction of the object on the plane and accept if it's the restriction of a bivariate low degree polynomial of total degree at most. So that's the Ras-Safra test. And they were in fact able to prove a slightly stronger result, but for the other test, for the plane point test, they were able to prove that if epsilon naught is, they were able to notice this result is almost similar to the Arora Sudan result, except that here Q needed to be at least omega to the d power 4, whereas in the Ras-Safra case, Q needed to be only linear in D. And it came at a cost. It came at the cost of querying a plane instead of a line. That is, you had to query Q square points instead of just Q points. You increase the query complexity from Q to Q square, and you are able to get Q to be omega D. And since then, and both these results are both the Arora Sudan and Ras-Safra results were used to construct PCPs with extremely good error and stuff. And these were instrumental to construct PCPs in the late 90s. And since then, there's been a lot of improvements and subsequent improvements in the world of low degree tests. I must mention one thing about Ras-Safra. Why did they move from line point to plane point? A crucial property that they would use in their test is if you take two planes, these two planes intersect on a line, and the intersection is itself a good code. When the function restricted on the line is also has distance on it. They would use this property over and over again in their proof.
So in this theorem, the way the parameterization works is Q is not the query. Q square is the query complexity.
Q square is the query complexity. Q is the size of the field. So Q is the size of the field.
Okay.
Throughout, yeah. FQ, yeah. Q square is the, yeah. Okay. Questions? And since then, there have been several improvements to the low degree test. I'll mention a few of them. One was asking, one set of results was asking, if you really, for example, if you had to pick a random line, that means you have to pick 2 points at random in the Rubenfeld-Sudan setting. If you are in the Ras-Safra setting, you have to pick a plane. So you have to pick 3 points at random and pick plane. Whether you really needed this so much randomness, or could you do it lesser amount of randomness? There were tests due to Bensason, Sudan, Vardhan, and Avi. In 2003, we sort of de-randomized the low error regime of the line point test. And then Moshkowitz-Raz in 2006 gave a de-randomization of the Ras-Safra plane point test. So this was de-randomized, showed that you could do it with far lesser randomness than needed. You just needed one random point, and the other two could be sort of de-randomized points. That's what both these results sort of show. Then there was Ramon's question about what happens when you look at small fields. All of these results which I talked about was for large fields. This was first investigated by Lohan, Krivolovich, Kaufman, Litzen, and Ron, 2003. They proposed the test which I mentioned. Pick a random D plus one dimensional space and check if it's this one. The test, an optimal analysis of this test was given then by Bhattacharya et al. And subsequently, this was then extended to this. Both the first two results are only for GF2. And the Haramati-Shpilka then extended it to all constant size fields. Actually, I forgot to mention there's another result of Kaufman and Minzer, more recent result, which gives an alternate analysis of the Haramati-Shpilka Sudan. So this was for small fields. The other thing is question which Yotam asked about the dependence. How small can epsilon be? Basically the value of tau over there. And there was a paper by Amay Bangale, Irit, and this is in no, in 2017, which answered, tried to get a better Q versus epsilon dependence. But this came at a cost. They couldn't analyze the cube plane point test. They went to an even larger object, the cube point test. And then for subsequently an optimal analysis of this test, there is basically not an optimal analysis with respect to the Q versus epsilon dependence was given by Minzer and Zhang last year. So they gave the right value of tau for the cube versus point test. But this came at a cost. To understand this, they had to go to a cube versus point test, and we don't know of similar results in the plane versus point or the line versus point test. So these were these improvements. So just looking at the state of affairs, this was the original Polishchuk Spielman or the Friedel-Sudan result in the low error regime, which I flashed. Then once you go to the higher error regime, we had the Arora Sudan result, which worked, which also took the line point test, which worked only when Q is quartic in D. If you to get Q to be linear in D, we had an alternate test, which was a Ras-Safra test, but it worked with a plane point test. It didn't work with a line point test. And this is more or less modulo the improvements which I flashed the previous slide. The state of low degree test was more or less this. This was what we knew best of the low degree test. Naturally, to give, is there a common strengthening of all this? In particular, can we get the result that Ras-Safra gets for the line point, for the plane point test for the line point test? In particular, can we get a line test which has Q to the omega t? This would sort of give a common strengthening of all these three results. It's natural to expect this. One could conjecture that this is true. But for various reasons I mentioned, that is basically, there have been two techniques in proving these sort of proofs. There's the algebraic or the polynomial method, which happened in the proofs of all the proofs that came up to the PCP theorem, and subsequently Polishchuk Spielman, Friedel-Sudan, Arora Sudan, and so on. Then there are these combinatorial things, which basically the only algebraic property they will use is the fact that the intersection of two planes is a line, and on a line, a polynomial has large distance. There's non-zero, a non-zero polynomial is non-zero large fraction, and then no more algebra. The rest of the proof combinatorial, and actually all the subsequent improvements which I mentioned use this particular fact.
And the expansion structure.
And the expansion structure of the graph. But that was actually used in Friedel-Sudan, Arora Sudan, also used. When they used the expansion properties of the underlying graph and this property. Question was, once again, what we want to ask is, can we get a common generalization of this? And notice that the fact is the line point test, all proofs of it used only the polynomial method or algebraic techniques. Since Ras-Safra is this one of the sort of combinatorial proof, most subsequent improvements use the plane point test or even further extensions of it, the cube point test, and they give better and better analysis. But still the line point test seemed unanswered by this. And our main result is basically, we do get the same result for the line point test with Q equals omega t. And in some sense, as we mentioned, it's sort of a return of the polynomial. We can't appeal to this combinatorial techniques which Ras-Safra introduced. We need to go back to the polynomial method. It's both the return of the polynomial method and low degree test. It's also, if you look at it's a sort of return of Madhu to proofs of low degree test in some sense. This polynomial method made it come back to low degree test with Madhu coming back to. So basically this work, there's a question Madhu had suggested to me back in grad school, early 2000s, very annoying, didn't manage to prove it. So Madhu visits TIFR once a year, he visits Bombay here. So last year, sort of one of his visits, he thought we'll revisit this old problem, and that's how the skin got solved. Yeah, so the result is basically this. It's the low degree test in the higher regime for the line point. Yeah, that's the statement of the result. There is, I should have mentioned, tau is some fixed constant. Think of it as 1/50. We don't make any efforts to optimize what tau is in this paper. That's a worthwhile goal to understand what tau is. Believe tau should be half. I don't know how to prove that for the line point test. For the cube point test, that has been proved by Minzer and Zhang.
With tau equals 1.
With tau equals 1, yeah.
So why do you believe it should be half?
I think for this one, it is, you can't, there is a counterexample with half, no? If you go to the line point test.
Is that? Okay.
I think so, yeah. I think so. Anyway, yeah, but I'm on, being recorded. Yeah, so that's the main theorem. Any questions on this? So what I will do in the remaining talk is give some of the ingredients that go. In fact, the chief ingredient that goes into how we use polynomial method to prove such a statement. Yeah,
I had some question about when you talked about the combinatorial approaches,
Mhm.
what about low degree functions are they using?
The only fact that they use is the low degree functions on lines from a code. It is a non-zero low degree function on a line is non-zero most of the time. That's the only property they use. And then low degree polynomials disappear for a large fraction, and they possibly come again when you do some spectral analysis later on. Even there, low degree polynomials, I don't recall. That's the only property of low degree polynomials that they use.
Spectral analysis is more about how the graph of plane versus plane looks like. Spectrum.
Yeah. Yeah, so that's the Rasa thing was, in some sense, it's nice. It captures this property of low degree polynomials and then forgets what this one, and then you go on to purely combinatorial techniques. But if you want to understand, somehow this didn't work for the line point test because two lines intersect at a point and you really don't have any distance or anything over there. You need some, at least the current techniques failed to work there. And this was why it was a challenge to understand how does a line point test work in the higher region. Question? Okay, so let's try to give a high level overview of one of the ingredients that goes into the proof. So just to recap Friedel-Sudan's analysis, this was the low error regime. This was a statement they proved. And the technical backbone behind this statement of Friedel-Sudan was actually the Polishchuk Spielman lemma for access parallel lines that I mentioned. So let's actually look at that a little more closely and see if we can strengthen that lemma to prove the corresponding statement for the higher error regime. So Friedel-Sudan proved a statement. This is in the low error regime, and the tool was the Polishchuk Spielman lemma. So what I'll do in the next 5-10 minutes is we'll look at Polishchuk Spielman lemma, see if we can strengthen it to prove the corresponding higher error version. So what is the Polishchuk Spielman lemma? Polishchuk Spielman lemma is a statement about, there's the following statement. I'm going to state it as, for people who are familiar with it, this is going to be stated in a slightly non-standard format. It's equivalent, but in non-standard format. So in a format that I can generalize shortly. So what's, even before, what does the Polishchuk Spielman lemma says? Polishchuk Spielman lemma says, it's going to say the following. Suppose you're given a bivariate function. You're given, you're working on a plane, and you're given two polynomials. There's polynomial a1 of xy and a2 of xy. You're given two polynomials on the plane, and you look at several columns in the plane, the restriction of both these polynomials to several columns. You know that once you restrict to this particular column, which is basically setting x to a particular value, a1 divides a2. And the same thing is true for several rows. If you set y to be a particular value, a1 divides a2, then I want to ask, is it true that a1 actually divides a2 even in the bivariate setting as a bivariate polynomial? And Polishchuk Spielman says, gives you sufficient conditions for this to happen. Okay, so let's state it. So these are the two. So I'm going to introduce a third variable because it will be useful for us. But these a1 and a2 are basically the two polynomials I just now mentioned. So suppose you're given a trivariate polynomial in which the z degree is 1. The z degree is 1. And you're given two sets. These are basically the set of rows and set of columns. UV of size of enough number of rows and enough number of columns, such that for every column, for every u in this set, there exists a degree d polynomial such that this basically says that a1 will divide it. This is the same as stating that. Basically, if you plug a, u, y, c, I'm stating that there is a polynomial for z I can plug in y, the remaining variable, such that this becomes an identity. So all I'm claiming at this point is a1 uy cuy plus a2 uy is identity. So it just means that a1 divides a2. So for each of the rows, each of the columns, we have there's a polynomial that witnesses that a1 divides a2. And the same thing happens for the rows. There is a polynomial that shows happening, and there are a large number of such rows and columns. Then what Polishchuk Spielman conclude is actually that a1 divides a2 as bivariate polynomials.
What is capital D in terms of?
What is the capital D? I should have said. No, so this, no cap, the way they stated, this is all I need is if whatever this D is, this has to be at least twice D.
But D is what you, D.
D will, this is the Polishchuk Spielman lemma holds good for any D, but D will typically eventually be linear in D, in small d. We will set D to be linear in small d. When it's applied for the Prahladh Sudan application, D will be, capital D will be set to linear D, but over here D and capital D are free variables. Okay.
So the way I read it is that you have some condition in mind, like A1 divides A2.
Mhm.
And now you program it in some Python language into this polynomial method format.
Yeah. Mhm. So this is all. Previously we were looking at local versus what you need to. I'm trying to say it in different words. This is local versus global. You're going to check. There's a global property of being low degree. You were checking it on lines, and you had. Now here that was in the property testing scenario. Here, the property I'm looking at here is A1 dividing A2, or the fact that AXYZ has a root of the form Z minus QXY. Here I claim locally, when I restrict to a particular variable, when I go to a smaller dimensional object, then in fact this is the case. And it's perfectly the case for all of these. If this happens most of the time, not even most, here I'm saying if it happens, this is an equivalent way of stating most of the time. It happens for a large number of ones. Then it must be the case that globally also A1 has to factor it. A1 has to divide it. So that was what the previous things were in the more common property testing world. This is more in the algebraic world. If AXYZ, when restricted to rows and columns, does have A1 divides A2 in that sense, then it must be the case that A1 has to divide A2 even as a bivariate object.
It's not enough just to check to the values of X or Y.
It's not enough. It's not. If just X, we'll see this. So I could just give
X appears
XZ minus CY. So for most values of X, this is in fact, it's divided, there is a polynomial in Y that anything non-zero in X, there's a root of the form Z minus CY, but there is no bivariate root of the form Z minus Q of X Y for this polynomial. Okay. The two directions are necessary for Polishchuk Spielman. One direction will not suffice. Yeah. Yeah. So given that Polishchuk, so that's the Polishchuk Spielman lemma. Flash there. This led to the first nearly linear sized PCPs, and that was because the relationship between that D. What Avi was mentioning, this D was linear in small d, and the size of the field had to be only 2D compared to D. Everything was linear, therefore this led to the first nearly linear sized PCPs construction. Polishchuk Spielman used it to construct PCPs. It also formed the technical core of Prahladh Sudan. I'll not get into this for this talk, but that lemma was the main technical core of it, and it is proved using properties of the resultant, of an object called the resultant.
I'm very sorry. I think I don't understand this assumption. 10D degree at most large D.
10D degree is, I'm going to view this polynomial. This is a polynomial.
Yes.
This is a weighted degree. So
okay. So Z gets degree small d.
V gets degree small d. X gets degree 1.
Yes.
Y gets degree d. So I want both the 10D degree and the 01D degree. Sorry, I should have mentioned that. It's some notion of weighted degree we were working with. And Polishchuk Spielman was sort of crucial for this. Polishchuk Spielman lemma was crucial for Prahladh Sudan to get the improvement from Q to be linear in D. They used the Polishchuk Spielman lemma to get that. The previous analysis of low degree test required Q, which was at least cubic in D, to analyze the line point test. And they sort of used this line. I don't think I have time how they do it, but believe me on it, this is how they're going to use the Polishchuk Spielman lemma. Now, I would like to sort of strengthening of the Polishchuk Spielman lemma to prove the higher error version of the low degree test that we're trying to do. So one thing we could ask is, can we prove a similar such statement for A's in which the degree in Z was not 1, but more than 1. We ask for a similar statement. So one conjectured statement is suppose A is some polynomial with degree dz greater than 1. Think of dz being 2 or 3 or something, just mildly larger than 1. And you just have the similar statement. You have rows and columns of large enough size such that for each of the columns, you do have that a root. Once you restrict one variable, you do get a root of the form z minus cuy along the rows. And similarly, along the columns, you have such a root. Does that mean that actually there is an honest to God root of the form z minus q of xy for this polynomial? This is what I would like to ask. And the very similar reasons to what Zeb asked. There's this statement as in this format has a counterexample to it. Particularly, you could come up with a polynomial axyz, which is xz minus cy, yz minus rx. This is just the degree 2 version of this polynomial. Notice that for a large settings of, for any x which is non-zero, there is a root of the form z minus cy by this one. Similarly, for any y that is non-zero, there's a root of this, but there is no root of the form z minus q of x.
This quadratic in Z.
Huh?
It's quadratic in Z.
Sorry, I didn't.
The degree of Z is 2.
Yeah, the degree on z is 2. The degree on z is 2. So this was a counterexample to this conjectured statement. And I could give the same answer which I gave to Zeb. There I needed 2 directions. Polishchuk Spielman. One direction did not suffice. So here, similarly, if you were looking at degree in Z to be 2 directions would possibly not suffice. Possibly if you had 3 directions in which, that is when you restrict to 3 different directions. In fact, its axis parallel doesn't make any sense. This one, you're looking at 3 different directions. Possibly the way to get around is for a large Z degree, dz, need at least dz plus 1 sets of parallel directions. If suppose the result were true for all those dz plus 1 parallel directions, then can we prove such a similar statement? And morally, this is what we sort of prove, except that we don't get dz plus 1, we need a larger number, but we show if there are enough number of parallel directions on which, when restricted to those parallel directions, you do have a root, then globally also you have a root. That's going to be the high degree generalization of Polishchuk Spielman lemma. We're going to look in particular. What we'll prove is a high degree generalization of Polynomial lemma. In particular, we'll allow for a large number of parallel directions, not just 2. There's a counterexample. We should allow at least dz plus 1. We'll allow more than dz plus 1. So there's room for improvement over here. We believe it should be dz plus 1 should be the number of directions. And actually, the way I'm going to state the theorem, the lemma, I will not state it in terms of parallel directions. We'll state it as several pencils, concurrent pencils. Now, a set of parallel directions, a set of lines which are sort of are concurrent at the point at infinity. So I'm going to think of several. I'm going to look at it not as several sets of parallel. And here, in the Polishchuk Spielman lemma, there were 2 sets of parallel directions. One is things parallel to the x-axis and parallel y-axis. Think of these 2 as 2 sets of rays passing through point. We'll consider several sets of concurrent lines and state the theorem lemma for that. So what is this lemma statement? It's quite a mouthful, so let's take our time for it. So before, let A be some polynomial with the z degree, and the z degree is not 1, it's more than 1. And here I'm going to look at the weighted 1,1d degree is at most d. So I'm going to count x as 1, y as 1, and z as d when I weight, and the weight of degree is 1. And there's a large set of points. Each of these points is going to correspond. You're going to look at rays passing through these points. There are a large set of points f square of at least 2 dz dq points, such that for each of these points, there's a large fraction of directions, such that if this is a mouthful I'm saying, that is basically what it's exactly what I've said. That is, each of these points, there's a large set of directions, that is, and directions given by s alpha beta, such that for the point and the direction, once you fix the point and the direction, as I'm fixing alpha beta and uv. And so I'm looking at lines of the form alpha plus ut and beta plus vt. For every such line in this set, there is a polynomial p alpha beta uvt, so that when I plug that in, this becomes identically zero. That is, once I restrict to the line, then I get an identity. Then I want to ask, does there exist an honest to God? So, but when restricted to the lines, there's a root of the form. This polynomial has a root. Then does it also have a root in this word? That's exactly. Yes.
Sorry, how are these parallel directions again? Like, can you?
These are not parallel directions. These are not parallel directions. These I'm going to. But I could have done this thing for parallel directions also. It will be convenient for the proof to have all the lines passing through a point in the affine plane and not the point at infinity. Yeah.
So
But these are equivalent statements. Yes.
So what you prove is in fact true for the axis parallel setting and not just the line point setting.
No, not axis parallel, because I would need far more than axis parallel. Right now, I'm only stating the bivariate case, by the way. So I'm looking at the bivariate case. So if the degree in Z is say 2 or 3, I will need at least 5 to 6 sets of lines. So one's parallel to the x-axis, y-axis, and possibly 45 degrees. Several such things. If I have them along all those directions, if I have the statement, then I will be able to infer it globally. Questions? So it's a mouthful, so let's just stare at this for a while and see if you follow it. Exactly. Yeah.
So you're saying ideally you'd like the number of points to be 2dz plus 1 or something?
Yeah, the number of points would be d, in fact, exactly dz plus 1.
But the number of lines to reach is still depend on big D.
It will be dependent on big D, yes. I should have been able to prove this, we don't prove it. So, yeah. Okay. Yeah. So it's a sort of statement I want to, when I write it in words, it takes this one. It basically says there are several lines so I'm looking at the function ax, y, z. Z it has a moderate degree in z, say 2 or 3. 10 or it's a some fixed constant dz, and when you restrict to several lines here, you do have the fact that it has a nice factorization. It has a nice root of the form z minus q. Because when you restrict, go down to the space from bivariate to go to your one dimension lower, then this trivariate polynomial, which is now a bivariate polynomial, then will have a root of the form z minus pft. And I want to say, if this happens, it should be the case that globally also there is a root. By the way, this should remind you of Hilbert's. Yes.
What if the root is oh, sorry.
This should remind you of Hilbert's irreducibility. If something factorizes globally, the factorization will more or less continue for most random ones, and this is what we do. Except that you want. That's how actually Arora and Sudan proved their original statement. But we want to follow the parameters tightly to show that Q is linear in D. If we do just a straightforward application of Hilbert's irreducibility, Q will be polynomial in D. Okay. Is the statement clear? We'll give a sketch of how we prove this in the next 5-10 minutes. Okay. Once again, so if you have a trivariate polynomial, so the restriction of several lines, and these lines are of special types, they are lines passing through several confluent points. Then you have that there is a root of the form z minus p. Then globally also there's a root of the form z minus p.
So, Prahladh,
yeah.
Are you going to describe how this lemma relates to the low-error analysis?
So how I'm going to relate is this. I'm not going to do it, but just when we ask the question, what we will do is so let's think of the lower analysis only on the plane. Forget about the m-dimensional case. Just even on the plane, the line point we don't have a higher proof. So you're given, so for every line, you're given a polynomial. So you're given the points table for a plane. And for most lines, you know that the function is actually close to being low degree. Close to, in the sense 1 over 10 frac. Then from that, we are going to construct this trivariate object using the points table. This is sort of the algebraic explanation for why the points table succeeds. We're going to construct the points table. And the points table will have in its belly, for several lines which are passing the test well, it will have these features. And then we are saying, once you give this algebraic explanation for the points table, hidden in the belly of that is the actual Q of xy, which is the honest to God low degree polynomial, which That's how we're going to do. There's some in this, if people are familiar with sort of Sudan's algorithm or Guruswami Sudan's algorithm for this decoding. There's first an initial step, which is the algebraic explanation of the data, and then you do something to factorize, show this one. That's the one part which I'm ignoring is how do you explain the AXYZ will sort of try to capture the entire points table on the plane and the success of the low degree test over there. And then we'll show that because that captures it, if there are several such lines, there must be in its belly all the low degree polynomials which explain. I'll skip this one. This was the reason I'm skipping it. This was standard. This is already there in previous works. The new version is firstly, this statement is new. This lemma statement is new. The high degree version of the Polishchuk Spielman lemma, and the proof of it is also a new proof. Okay, so let's see. Let's see a sketch of this. So once again, this is what we have. So once again, this is going to sort of answer Zev's question about I have several such sets of concurrent lines. I want to say I can do the work from one set of concurrent lines, but I do not know if any one of them is good. So I'm going to define a notion of goodness, and then we'll show that there is at least one good thing, and then we'll focus only on that particular set of concurrent lines and throw out all the rest. So what is going to be a notion of good? Notion of good is going to be, we'll say one of these points, alpha beta is good, is the following good. Basically, if you look at the polynomial in Z, when you plug xy to be alpha beta, this polynomial should have no repeated root. When you view it as a polynomial in Z, I don't want it to have any repeated root. Alpha beta Z, the A of alpha beta Z. So this is a polynomial in Z, the single variable Z. I don't want it to have any repeated root. Now, this is a condition. Now, why does there exist such a point? This one, this is just the condition, that is, you can write down another related polynomial to AX, Y, Z called the discriminant with respect to the variable Z of A. And as long as the discriminant is non-zero, this discriminant will be a function of only the remaining variables. Once you take discriminant, forget about what this one is, forget what this fact means. This is some polynomial in the other two variables, X and Y. As long as it's non-zero, it will tell you that for every whenever it's non-zero, the corresponding A alpha beta Z will have, when viewed as a polynomial, that has no repeated.
Can you remind us what the set big B is?
Big B is just it's all these points, the centers of the roots of the various rays. And because the root is large enough and the number of B's are large, and to compare to this, we will have, exists one good point. So we'll just work on that particular point, that particular root and the corresponding rays associated. We'll focus on it. Then I want to show from this, we can still recover the. So, and let's do a change of basis. We'll just assume this point alpha beta for the rest of our analysis is actually the origin, 0, 0. So what do we have now? We have that this origin satisfies that A00, Z has no repeated roots. And there's a large set of directions such that passing through that, basically now lines are of the form UT, VT, because you're looking at lines through the origin, for which you have this property. And let's furthermore assume that all of these lines take the same value at the origin. This is only going to divide the number of lines by a factor of the Q, and that's okay with us. We can divide it by the, they all take the same value at this. Or let's just take the most popular value among them. So what do we have about this? We have that, firstly, because this is, we have A00, P0 is 0. And furthermore, and A00, Z factorizes for distinct, possibly you have to go to some extension field, but it then factorizes this, and these are distinct roots. This is what we have. So exactly one of these will satisfy that P0 is gamma I, because we know what P0 is. So let's focus on a particular line. Exactly one of them will be P0 as gamma I. So we know that we had an original equation. We had this equation. We are in the search of this equation, Ax, Y, Z. We want to know if it can be factorized as Z minus Q of xy into, say, some R of x, y, z. we are in search of such a factor of the form z minus q of xy. Now, when I restrict to a line, there is this one factor will be a linear factor, and we know which of those linear factors it is. So you go mod, set x and y to be 0, you go mod xy, then we can identify which of the z minus gamma i's is actually going to be lifted to this point. This might not be clear, but this is basically what you're going to basically do Newton's iteration, or what's also called Hensel lifting. We have a factorization of a polynomial in the univariate when x and y have been set to 0. That's this. Now we are going to slowly. So this is basically taking this, writing this from polynomial axyz mod xy. That's exactly that equation. Now I will lift this equation to mod xy square, mod xy cube to larger and larger powers. Large enough such that now this becomes a polynomial identity, at which point you can actually pull it out. This is Hensel lifting, and we are just going to look at Hensel lifting first one. And furthermore, what we have that this is a root, but gamma is not a root of the derivative itself. So let's extract this root one. So we already know that this polynomial satisfies this. Let's see how we can extract it. We know this already, this particular line, but let's extract this one. We know AUT, VT, PT is identically 0. In particular, it's identically 0. It's also 0 mod t per k plus 1 for every k. K equals 0 is exactly the equation which we had previously, which was k0, 0, gamma is 0. Let's see what happens when k equals 1. This equation, I'm just going to write Taylor series about the point a0, 0, p0. It's just a0, 0, p0 plus ut into the x derivative plus vt into the y derivative plus p0, p1t into the z derivative mod t square. Now notice here that because dc a0, 0 gamma is non-zero and everything else in this is known, I can extract p1 uniquely from this. That's a unique way in which I can pull out p1 from this equation. This equation I'm basically writing AUT, VT, PT equals 0 mod t plus 1. I'm writing it in, this is Hensel lifting for Newton's iteration. You can extract p1 and thus pt mod t square. And this process just continues. You can show that as long as the derivative is non-zero at this point, which we have guaranteed as a goodness of the point, we can, in particular for general k, we can always extract a root which has this property. AUT VT is 0 mod t per k. We can keep this, and there's only a unique way in which you can, doing this, we just keep extracting this. Notice all these equations are only work mod tk plus 1. They are not polynomial identities. They work only in the modular world. But we know that once we go to t into d power t plus 1, these two things have to match because there's only one. We particularly know PUVT is a polynomial that satisfies this. Therefore, if you keep doing this, when you come up to degree d, the polynomial you do get should be on the line, should be exactly the polynomial PUVT which we had. That's fine. This is all. I'm doing the univariate. I'm just doing Newton's iteration on a particular line. But Newton's iteration could have been done not just on a line, it could be done on a plane too. And we could do the bivariate Newton's iteration. And it also requires only, the starting condition is only these two. You can do exactly the same Newton's iteration. Particularly, you will get, you're going to go AXY, QFXY, 0 mod XY, K plus 1. We'll go from, keep increasing. We know it. When k is 0, we know the statement, that is a0, 0, z, and we keep increasing k from 0 upwards. We can find such bivariate polynomials, unique bivariate polynomials as you keep going. So this particular bivariate polynomial, we know we have a unique bivariate polynomial. So if you in the bivariate polynomial, if you substitute the line, you should get an identity. There's no other go. That's what you got. But you know there is only another polynomial that satisfies this, PUYT. Therefore, these two polynomials should exactly be the same. But what did I say? This polynomial phi of d, what you get by the bivariate interpolation, should be what you get by the linear interpolation. Yeah, let me done that. Yeah, so far fine. This is just says you can do Newton's interpolation or Hensel lifting so that you solve all these modular equations. Notice that finally, I don't want to solve a modular equation. I want an exact polynomial identity. How do we go from modular identity? Newton's iteration will give you some give you solutions of this form. I want to remove this mod xy to the k plus 1 because I want an identity of this. So we want q of xy, not something mod xy to the k plus 1. But we do have this, we have a of xyd, we have this particular. How do we know that this one is actually, we don't know such a root actually exists at all. But what we know is when we restrict this to several lines, this is actually not just an modular equation, it's an identity equation. That's what's given to us. So in other words, our candidate, we can ask if phi du xy, the polynomial gets actually the final polynomial you want. Is it this one? Does it actually satisfy even the polynomial identity, not just a modular identity? And answer is yes, because for several lines, you know that buy, if you restrict it this way, buy is 0 for each of those lines. Therefore, this should be, and you know, for several lines passing through this point, you have this identity. Therefore, Schwarz-Zippel will tell you that it has to be an identity period. And that's will give you the. So it's sort of just using polynomial method a couple of times, and you get, and do a careful Newton's iteration. This Newton's iteration is standard in this one. Doing Newton's iteration very carefully, realize that the bivariate interpolation, when you do bivariate lifting or univariate lifting, you get the same polynomial and then use Schwarz-Zippel to show that the thing that you get out of bivariate interpolation is exactly what you would have got on each univariate line.
Is the VDZ what controls how high the error is? Like
Which one?
D sub Z.
D sub Z will be how high the error is. So yeah. So for less than around half, we'll need the DZ to be 2, and DZ will be that constant. But yeah. So DZ will be typically, I would have thought it to be order 1 over epsilon. Our proof gives, I think, order 1 over epsilon square, because the DZ, the degree in Z will be order 1 over epsilon square in our proof. Yeah, recapping what we show is, firstly, we give a high degree generalization, Polishchuk Spielman lemma, which then gives and yields a soundness analysis degree test. That was this statement. So in some sense, it finally yields one thing which was missing in the low degree test literature. It gives a common strengthening of the lower Friedel-Sudan result and the 2 higher results. It gives one common strengthening this result. So this is a low degree test result, which implies all the other tests, sort of with the return of the polynomial method.
So Prahladh, so these the lower results, Arora Sudan and Ras Safra, they were presumably for some PCP applications too.
Yes.
So does this new analysis simplify those results?
So wherever you could have used that, you can use this also now, but doesn't yield any new result per se at this point of time. It doesn't. So because you already have de-random. So when will a line point test be useful over a plane point test if you care about the rate? Because that's one. But there are already been de-randomizations that were done. So in some sense, because of de-randomization, line point is not any more useful than plane point. So at this point, I don't have an application of the result. It was more the fact that if this was true in such a way, there should be a common strengthening of it, and we didn't have one. And it was primarily because we did not know how to use the polynomial method to prove this, and we now.
Okay, in the interest of time, I think